afternoon, everyone. My name is Professor Andrzej Zwelendowski. I'm head of School of Mathematics and Physics, which hosts Lincoln Math and Physics Week 2021. This event is a part of a British Science Week, which runs from 5th of March, started last Friday. This is our second day and our fourth lecture in this series. In the beginning of each lecture, I give you a short welcome, which is basically almost the same for every single lecture, because some people come on one talk, other people come to another talk. If you come to every single talk, after this introduction week, you will know probably my words by heart better than me. Traditionally, when you come to our public lectures, which our school hosted already for several years, it will be in our lovely campus in the center of Lincoln by the waterfront, which was already port in Roman times. Now city is modest size, 100,000 inhabitants. This quite old city was founded by Romans already in the 1st century AD, just few years after Romans came to the British Isles. Once it was a base of a famous 9th Legion Hispania before the legionaries moved to York, and the place became a place for retired legionnaires, and it received the prestigious status of colonia already in times of Emperor Domitian, and it was a very comfortable place for retired legionnaires to live. Even now, you still can see remains of Roman times, like you can walk or drive under the surviving Roman arch. In fact, the only Roman arch under which traffic still allowed in the British Isles. The next big step in Lincoln development came about 1,000 years later with another visitors, the William the Conqueror and his team. Then they came. They found that the spot which Romans considered as an important strategic place is good to build a castle, and famous castle of Lincoln was built. And opposite to this castle was built even more famous cathedral, Lincoln Cathedral, which some consider being the most beautiful cathedral in British Isles. And probably one of most beautiful, in fact, on Earth. And for sure, it was for a substantial period of time, about 200 years, the tallest building on the planet when a wooden spire was still in place. As cathedrals, the oldest seat of learning, already from Middle Ages. However, university was open in Lincoln only at the end of 20th century. Then the first building was built in a beautiful waterfront. And since then, university grew quite a lot. And our School of Mathematics and Physics still perhaps the newest school in the United Kingdom, which was built from zero in this ancient city, but modern campus was open in 2014. We share our base building, named after another famous person from Lincolnshire, Isaac Newton. In this building, named after him, we share it with School of Computer Science and Engineering, and our building will be just 4 years next month. As our lectures are primarily aimed at those who study A-levels, but not only. They also accessible to everyone who is interested in mathematics and physics. And I, of course, tell, as we host an event, what study of those subjects we have here in Lincoln, in case somebody wants to continue after A-levels to study the subjects. We have a full range of degrees, bachelor and integrated master degrees, both in physics and in mathematics. We also have joint awards with computer science, or with another Asian discipline, one of the most Asian disciplines, philosophy, mathematics for philosophy, physics for philosophy, and we also have a mixture of mathematics and physics in a joint degree. We also, of course, have research degrees. We all do science here, and that is the purpose of this week, to shine some light on local discoveries in this discipline, mathematics and physics, we do here in Lincoln. And with that, I'm very happy to be joined with our speaker tonight, Dr. Claire McIlroy. Hello, Claire.
Hi, Andre.
A pleasure to see you tonight. And we all are looking forward to your presentation. And I just say a few words to introduce you. Claire joined our school quite recently. In 2019, Claire moved from University of Nottingham as a holder of personal fellowship with a very long title. It is called Royal Commission for the Exhibition of 1852 Fellowship. And the ones who, of course, I don't think there is anybody present in audience who remember that exhibition personally. But exhibition of 1851 was exhibition to basically exhibit all the wonders of Victorian British technology, science, everything. In those days, it was really a revolutionary idea. In the times before, we have all this kind of congress centers and stuff. So it was first ever such kind of event. And there were lots of criticism and that is it worth doing that? And there was special commission assembled to organize this exhibition. And in fact, people feared that it will be total disaster, you know, loss of money, everything. However, exhibition had been so successful that commission actually had a bit of money left, which even a little bit left till nowadays, when from this money they continue help science by, for instance, awarding these very prestigious fellowships, and Claire was holder of one of those. And now her fellowship is finished, and she moved to the post of a lecturer in our school. But just tell a little bit, a couple of more words. Claire is mathematician by training. She received an integrated master's degree in mathematics from University of Leeds. And after she stayed there to do a research degree, so-called PhD, doctorate, in applied mathematics as well. Applied means she applied it to the fields of basically everyday kind of life, and you will hear in your talk more. And that was about specializing in complex flow of complex fluids. So it's quite exciting. It's not only complex fluids, it's also complex flows. She obtained her PhD, and in 2015, after that, she moved for a research post in United States in Georgetown University in Washington, D.C. And after that time, she actually won this very prestigious Royal Commission for the Exhibition 1851 Fellowship in 2017. Tonight we will listen about how her research can shine some light on fancy three-dimensional printing. Welcome.
Okay, hi everyone, my name is Claire McIlroy. I am a lecturer in the School of Maths and Physics at the University of Lincoln. And today I wanted to share with you some of the work I've been doing on 3D printing. So I'm a mathematician, so I like to use a mathematical approach to improve and optimize various processes. So most recently I've been interested in manufacturing, so how we make things and how we can improve the things that we make. So whether that be making products that are stronger and more sustainable, or products that are more easily recyclable. I think these are really important questions that we should be asking and indeed solving for our manufacturing processes. So today I wanted to talk about a fairly new manufacturing technique, and that is 3D printing, or is sometimes called additive manufacturing. And in particular, I want to talk about 3D printing with plastics. So plastics, and in particular single-use plastics, have had pretty bad press recently due to the impact they're having on the environment. But actually, if we can make plastic products that are stronger, more sustainable, more readily recyclable, then this is potentially a better solution to some of the non-plastic alternatives that are being proposed, which each have their own environmental issues. So these properties, so strength, durability, recyclability, all come down to the properties of the plastic material itself. So in particular, the microstructure of that plastic and how that behaves during the manufacturing process. So hence my title today, we're going to look at 3D printing under the microscope. However, plastics are incredibly complicated materials, and it's very difficult to visualize the microstructure or individual molecules as they traverse quite a complicated manufacturing process using something like a microscope. So today I'm going to show you how we can use a mathematical modeling approach to really understand what's happening at a microstructural level, and we can use this insight to solve some practical problems that we encounter with 3D printing. So there are a number of key advantages for 3D printing in manufacturing. So first off, it is a pretty cheap process, so you can pick up a decent desktop 3D printer for just a couple of £1,000. And actually Aldi was even selling a budget version in their middle aisle at one point. The ink or the feedstock that we use for this printing also comes in relatively cheap at £40 a reel. And it's also, in principle, relatively easy to set up. So there's very limited training costs associated with 3D printing. I say in principle because I'm going to show you some of my attempts at using the 3D printer a little bit later on. Next, 3D printing is additive. So this is in contrast to a lot of traditional approaches that are subtractive. So the idea is to make a product, you would start with a block of material and you would shape that block into your product by kind of cutting or grinding or drilling or removing material. So this creates a lot of waste. 3D printing, on the other hand, is additive. So you build up your product layer by layer using only the material that is required. So there's huge potential here to reduce the amount of waste material that's produced during your process. And then next, what really sets 3D printing apart from traditional approaches is the ability to make customized products, but on a really large scale. So for example, in traditional injection molding, we would have to make an individual mold for every single part that we wanted to produce. So this really lends itself to mass production, but it's very costly if you want to start making customized products. For 3D printing, on the other hand, it's very easy and there's limited costs with just printing a personalized design for each and every customer that comes through your door. So the possibilities are huge for customization when you're using 3D printing. So I wanted to start today by sharing some applications of 3D printing that got me really excited about the possibilities of this technology. So first off, we've been 3D printing prosthetics for quite some time now, so for humans and for animals, in fact. And I think this application really highlights how 3D printing can really create customized products that are fit for the user's needs. Another nice example in nature is that we've been using 3D printing to rebuild our coral reefs. Another example in the medical theme, it's common practice now to use 3D printing in tissue engineering. So the idea is you can 3D print tissue scaffolds and you can create quite complicated geometries that replicate a tissue or indeed an entire organ. And then the idea is that you grow cells on these tissue scaffolds that's been 3D printed. Now, if you choose the right plastic material to 3D print your scaffolds out of, you can make these tissue scaffolds biodegradable. So that means when you implant the tissue into your patient, that 3D printed tissue scaffold will eventually degrade away in the body. There's also a lot of interest of using 3D printing in the sports industry. So again, I think this highlights how we can really make personalized products depending on the athlete's requirements. And then using 3D printing with plastics, we can really start to focus on making equipment that's got enhanced protection exactly where you need it, whilst keeping the waste of that equipment at a minimal. 3D printing is excellent for making tools on demand. So I think every university experimental lab in the country will have a 3D printer on hand just to make and replace kind of small tools. So no more waiting for delivery if you break something. But this really comes into its own if you start thinking about taking a 3D printer into space. And so there's huge potential here to massively reduce the amount of equipment and the amount of weight that you need to take into space with you, particularly if you start to think about how you can recycle your 3D printed tools back through the 3D printer to make new tools. The Army is also really interested in 3D printing. So an example here of printing drones on demand in remote locations. Also a nice example of some 3D printed army barracks out in the desert somewhere. So we've now got the capability to 3D print much larger scale structures from concrete based materials. So this has really interesting implications, I think, for creating more affordable housing in the future. And then the final application I wanted to share with you today is a bit of a strange one, but we are now starting to see 3D printing emerge even in the food industry. So again, I think this really highlights how we can make personalised products for various individuals. So whether that's just making a custom design with some chocolates, or if you start to think about people's dietary requirements, perhaps adding medication to food, creating meat substitutes, or creating more palatable food for vulnerable groups. So the applications of 3D printing really are endless, and I'm sure if you go away, have a Google, have a YouTube, you'll find some applications that really excite you too. So let's take a step back now and think about what's going on during this 3D printing process. So the ink for this printing process comes, it's a solid filament of plastic wound up on a reel. And the idea is you feed this solid filament into a heated nozzle. So this is an infrared image of our printing nozzle extruding some material onto a build plate. So the nozzles are really hot, so they operate at typically around 200 degrees centigrade. So they're hot enough that solid filament gets heated up and the plastic becomes molten and can start flowing through that nozzle. So the molten material flows through the nozzle until it reaches the nozzle axis and then can be extruded or deposited onto the build plate. And the idea is the nozzle can move around in the XY plane distributing this material. Now the trick is you need to cool off this hot molten plastic fairly quickly, otherwise it's just going to kind of flow and spread out on your build plates. So the trick is to cool it down quickly enough that you deposit a nice cylindrical filament onto your build plate that you can then start building on top of. So the idea is you repeat this process layer by layer to start printing a three-dimensional object. And as you can see, you can make quite complex shapes just by giving the 3D printer a CAD design. So what's the problem? So it turns out it's quite difficult to make your 3D printed parts look like the CAD design. So as I said before, I'm a mathematician. I did not spend any of my time at university in the labs doing experiments. I smashed way too many test tubes when I was at school, and that's one of the reasons I decided to take maths rather than one of the sciences. But nevertheless, we had a 3D printer in our department, and everyone thought it was a good idea that I should have the 3D printer in my office so I could start doing some experiments to complement my mathematical modelling. So I took the 3D printer, read the instruction manual, decided to give it a go. What could possibly go wrong? So this is one of my first attempts at just 3D printing a fairly simple robot design that I just downloaded off the internet. As you can see, it did not go well. My office also smelt like burning plastic for quite some time after doing these prints. So it turns out it's really hard to get your print settings right so that you actually print something that looks like the CAD design. So as you can see, after many trial and errors, kind of fiddling around with the printing conditions, I was finally able to get this little robot structure printed. So as you've seen, this 3D printing is a layer by layer technique. So we make these layered structures where there's lots of joins or weld lines between those deposited filaments. And it turns out these weld lines are notoriously weak, so they debond or come apart very easily if they haven't had enough time to weld together, or equivalently if you haven't got your print settings quite right. And so this is exactly what's happened to my robot here. The welds have just sprung apart and made this mess. And it turns out even if your weld visually looks okay, it's usually much weaker than what you would expect from your plastic properties. And you can measure this weld strength. So if experiments are your thing, you can start doing a mechanical test and tear along these weld lines and measure a tear energy. And this is always just much weaker than what you would expect from the bulk properties of your plastic. So this is a real problem for 3D printed products. So if we go back to our tissue engineering application I mentioned earlier, we need these 3D printed scaffolds to really withstand the weight of these cells as they're growing into a tissue. So if we've got these weld lines that are just going to spring apart as soon as they're put under some stress, and this is just going to be an absolute disaster for your tissue scaffold, which will just collapse under the weight of the cells as they grow. So we really need to understand how we can fix this problem. So we need to understand this welding process. We need to understand how we can define that there's been enough time to weld. So to really understand this, now is where we need to understand what's happening at a microstructural level. what's happening to the molecules during this welding process. So welding is essentially the molecules in that molten plastic interdiffusing between the layers before they solidify. So this is a molecular simulation of this welding process. So the idea is you bring together a yellow layer and a blue layer and you leave them for a certain amount of time, and you can watch how the yellow molecules interdiffuse into the blue molecules and how the blue molecules interdiffuse into the yellow molecules. And you can see as time goes on, the further they're able to travel across that interface and the better the weld becomes essentially. So if you had an infinite amount of time, then this interdiffusion process would eventually completely erase the weld line, so there would be no memory of there ever being a separation between the yellow layer and the blue layer. So in 3D printing, we don't have infinite time, unfortunately. So our time available for welding or for diffusion is determined by how fast your material cools down. So as soon as your molten plastic cools down and solidifies, that completely arrests this interdiffusion process. So all welding will stop once your material is solid. But remember, we need it to cool down fairly quickly because we want to keep that structural integrity of the filament that we're laying down. So there's a very fine balance here about cooling down quickly enough to keep your structural integrity while allowing enough time for the welding to occur to form a good weld or a good bond between those layers. We should also consider that we're not dealing with simple particles here. So we've got a molten plastic material, and the molecules in molten plastic are really big flexible molecules. So they're actually very long chains of carbon atoms all joined together, and these chains are very flexible, so they can change shape really easily. And the way they diffuse it depends on the shape of the molecule. So if your polymer chain kind of randomly coils up in a spherical shape, then it's going to diffuse around quite randomly. It's equally likely to move in any direction. If your polymer chain is somewhat stretched out though and aligned, then it might take this more kind of elliptical shape. So due to the asymmetry of the ellipse, it's going to be more likely to diffuse along its principal axis, just because it's easier to move in this direction. So the way the molecules diffuse are going to depend on this shape, and the shape of the polymers depends on the flow that it is encountered. So we know that this molten plastic has had to flow through this nozzle before being deposited on a build plate. So that flow through the nozzle can actually stretch out and align your polymer chains. So they're going to look more elliptical rather than spherical. So to understand our welding problem, to understand how the molecules are diffusing, we actually need to go right back and understand how these molecules are behaving as they flow through the nozzle. So what we need is a bit of fluid dynamics. So fluid dynamics is probably one of the oldest areas of applied mathematics. It's got a huge range of applications, from aerodynamics to predicting weather patterns and right down to understanding manufacturing processes. So if you were to come to Lincoln to take either a maths degree or a physics degree, you would have the opportunity to take a module in fluid dynamics. So this subject essentially gives us a rigorous mathematical framework to study, understand and predict how different materials flow. So fluid dynamics is based on Newton's second law of motion, so F equals ma. So this tells us that the total forces acting on an object must balance the mass of that object multiplied by the acceleration of that object. Or in other words, we can think of Newton's second law as telling us how an object will change its speed due to forces that are acting on it. So what makes things quite complicated in fluid dynamics is you can think of a fluid as a sea, if you like, pardon the pun, but a sea of lots and lots of interacting particles. So under this description, you have lots and lots of particles, each of which you can apply Newton's second law to. So as well as any external forces that act on the fluid, actually the way these particles interact will also tell you about the total amount of force within your fluid. So after some maths, we can derive an equation that tells us how this fluid will flow given certain forces. And this is called the Navier-Stokes equation. So in very simple terms, this is what the Navier-Stokes equation looks like. So on the left here, we've got the total amount of fluid forces in our fluid. And this balances the mass density of the fluid multiplied by the fluid acceleration. Now, if you've seen differentiation in your studies, then we find the acceleration of the fluid by taking the derivative of the velocity. If you've not seen differentiation, don't worry. You can think of this fraction as just the change in the fluid velocity divided by the change in time. So you can see exactly how this comes from Newton's second law, and this is telling us how the fluid velocity will change over time given the fluid forces. So these forces might be external, so it might be something as simple as gravity acting on your fluid, or it might be something internal to the fluid, so due to those interacting particles. So it might be something like a pressure or something like a viscosity. So the remarkable thing is that mathematicians are yet to find a completely general solution to the Navier-Stokes equation. What's even worse is that we don't even know whether a general solution exists. So this is actually one of the Millennium Prize problems where you will win $1 million if you can prove that these solutions exist, or indeed provide a counterexample to say that there are no solutions to this equation in general. So even though we can't solve this equation completely generally, we can apply it to our 3D printing problem and gain some insight to what's going on. So let's start by thinking about how simple simple fluids behave. So something like how a water would flow compared to how honey flows. So in the absence of any external forces, it's simply the viscosity of the fluid that determines how fast it will flow. And you can think of the viscosity as the friction between those neighbouring fluid particles in our sea of interacting particles. So if we've got something that has a very high viscosity, so something that like honey, and that's going to flow much more slowly than something that's got a lower viscosity, so something like water. So it's much harder for honey to flow compared to water due to that increased viscosity. Of course, we are not dealing with simple fluids. We have a molten plastic that's made up of these really long, flexible polymer molecules. And these flexible molecules give rise to lots of interesting behaviours in molten plastics. So first thing is that they are shear thinning. So this means the viscosity actually decreases as you flow them. So a good example of where this is used in real life is with paints. So with paints, the idea is you want them to flow really easily onto the wall as you're painting, but as soon as you stop painting, you don't want them to drip. So if you can start playing around with the viscosity, that's how we get these nice paint properties. These molten plastics are also what we call viscoelastic. So that means they show viscous and elastic properties. So a good example of this is with silly putty. So you can think about stretching silly putty out and making it flow or accessing that viscous behaviour. Or you can think about rolling silly putty up into a ball and bouncing it. And that's kind of the solid elastic-like behaviour. And these complex fluids also do really funny things when you start stirring them. So if we think about stirring a simple fluid, so think about your cup of tea in the morning. This is a simple fluid, it's essentially water. And think about what happens to the free surface of your tea as you stir it. So the free surface will always tend to dip down around your spoon as you stir it for simple fluids. But with these molten plastics that contain these flexible polymer molecules, they generate very different stresses that actually allow the free surface to start climbing up the stirrer in this rod climbing effect. So lots of different behaviours that we want to try and capture in our mathematical model of the molten plastic flowing through a nozzle. So how are we going to think about these flexible molecules mathematically? So the key is to think of each model as a couple of beads connected by a single spring. So this is called a bead spring model. So the idea is the two beads provide the friction of that molecule, or the viscosity if you like, and the spring provides the elasticity, so springs can stretch out and relax and give you that elastic-like behaviour. And it turns out we understand springs pretty well due to Hooke's law. So we know that forces in a spring is just proportional to the displacement of that spring, x. So we can represent our polymer molecules as this dumbbell, if you like, so we can get stretch and relax in a flow, and we can also get the dumbbell orienting in the flow as well. It turns out that these molten plastics are a little bit more complicated, and that's because there's lots and lots of these polymer molecules all at very high concentration. So the way I like to think of them is like a big bowl of spaghetti, really, where all these spaghetti strands are kind of really well entangled with their neighbours. So the way to think about this mathematically is we can still represent our polymer chain as a spring to give us that elastic behaviour, but this spring is actually restricted to this hypothetical tube region. So this allows us to restrict the motion of our polymer chains, because to move around, those polymers are going to have to slide around between their neighbours. So we capture this behaviour by using a tube model. Okay, so now we have a nice model to try and understand our 3D printing flow of a molten plastic material. So we can have some viscous forces in our model from our beads in our bead spring model. We can have some elastic forces in our model from our spring that's going to be restricted to a tube. And we know this has got to balance the mass density multiplied by the acceleration of our fluid just by Newton's second law. So we might want to solve our model analytically if it's simple enough to do. So get a pen and paper and go through the maths. Sometimes it's too hard to do this. So what we can do is start applying some mathematical methods together with a computer algorithm to derive an approximate but fairly accurate solution. So that is what I did for this model. And we can start to think about how our polymer molecules are behaving in our 3D printing flow. So the beauty of the model is that we can actually pick out and visualize individual polymer molecules in our flow. And so we've got my 3D printing nozzle here. We're depositing our plastic material onto a build plate, and you can see how the polymers become more and more stretched as they undergo this deposition process. And you can also see how the polymers kind of change their orientation as they go through this 90-degree turn. So what we end up with is this cylindrical filament that we deposited, where all the polymers are really stretched out and they're actually aligned in the flow direction. And then the idea is we want this deposited material to cool down really quickly. So because the printed material has to cool down really quick, what happens is all that alignment of the molecules is actually frozen in when your filament solidifies. And that's exactly what our model predicts. And it predicts that we get most alignment in this bottom region here. So we have this deposited filament where all our polymers are going to be kind of stretched out and aligned in this region here. So how do we know that our model is telling the truth? So we better check this with kind of some real data, if you like. So what we can do is we can actually measure some molecular alignment with what's called a birefringence method. So this is an experiment. It's a printed wall of filaments, so filaments stacked up in the vertical direction, and where there is bright light, that tells us the molecules are aligned, and where there's darkness, that tells us our molecules are kind of randomly coiled up. So what we see is that we get all this molecular alignment really localized to the weld regions between our printed filaments. And that's exactly what our mathematical model is predicting, and that we're getting this localized molecular alignment in this region near to the edge of each filament. Okay, so what does this mean for our welding process? So what's happening is as our molecules are coming through this nozzle and undergoing this 90-degree turn, all the molecules are aligning parallel to the weld lines in our 3D printed object. So here's a simulation of what's going on. So now we've got a blue layer coming together with a red layer, and the molecules are highlighted in green. So on the left, we've applied no flow, so the molecules are just randomly coiled up and they're not aligned. But if we flow them through that nozzle, then the molecules are going to become really nicely aligned parallel to our welds. So if we then start to try and pull our weld apart, these aligned molecules make it much easier to tear the weld. Or in other words, where we have the aligned molecules, the welds are much, much weaker. So our model is telling us that due to this alignment due to the flow through the nozzle, we're seeing this decrease in the weld strength. So now we're really getting somewhere, right? So we've developed a fluid dynamics model. It's based on the molecular physics of this molten plastic material we're interested in. And our model predicts that molecular alignment due to the printing flow is going to compromise our weld strength in 3D printed parts. And what's even better is that we've validated this prediction against some experiments as well. So what the beauty of modelling is now, we can predict the behaviour for any other print condition we like without having to perform any further experiments. So one question we can ask is what happens if we print faster? So if we print faster, we have to force our molten plastic through the nozzle at a faster rate. So that increased force is going to stretch out our polymer molecules even further. So we're going to get an increase in the molecular alignment with increasing print speed. So what does that mean for our weld strength? So if we have increased molecular alignment and increased print speed, this is going to decrease the strength of our welds. So printing faster is really detrimental to building up the strength between these printed layers. Okay, so problem solved. So what we've shown is that printing faster increases the flow-induced molecular alignment and consequently decreases the weld strength. So how can we fix this? So obvious answer, let's just print slower. But the thing is, if you go to your manufacturer and say, oh, we've solved your problem, you need to print slower. And they are not going to like that, because printing slower to them means reduced productivity and increased costs. So what's really nice about mathematical modelling is now we can start thinking about what other variables we can play around with to reduce this molecular alignment whilst printing at a print speed that's acceptable to the manufacturer's productivity. So I'll just leave you with a couple of variables to think about. So have a think about how print temperature might affect this story, and have a think about how the size of the molecules might affect this story as well. So just to go back to my 3D printed robot, so as I said before, I had to fiddle around a lot with the printing conditions to go from this disaster of a robot to something that looked more sensible. And actually that fiddling around and trial and error amounted to either reducing the print speed or increasing the print temperature to eliminate that molecular alignment and allow the welds to bond together much more easily. And then finally, just to remind you that there's lots of people out there printing much cooler things than my sad little robot. So this mathematical modelling approach is highly applicable to a range of applications from medicine to aerospace to military applications. So thank you very much for listening, everyone.
Thank you very much, Claire, for this wonderful talk.
Thank you very much for hosting, Andre.
Now we have time for a few questions. They can be placed either in a live chat in YouTube or in a Padlet link, which also you can find in this chat. And I'll just try to read those. So there is question in live chat. How useful is the biodegradable plastic in other scenarios? Does the biodegradability affect structural integrity? And could PHAs be used for printing plastic?
So yeah, one of the biodegradable plastics we were looking at is it's called a polycaprolactone. So this is actually a semi-crystalline polymer. So you get some interesting physics happening during the solidification process during the 3D printing that definitely affects the structural integrity. And this is what's used for the tissue scaffolds in the 3D printing application. So the idea is you can build up these tissue scaffolds using a 3D printer, place the cells on that scaffold, and then implant them in the body, and eventually that plastic will degrade away, which is really interesting. But yeah, kind of the more you recycle these materials, the more that affects the strength of those materials going forward. So yeah, there's a very fine balance between how many times you can process them and the strength of the materials.
Thank you. It's a probably related question. What is the smallest detail that you can print using plastic?
Wow, so the technology is becoming really advanced now, and they're getting down to really looking at nanostructures. So kind of single filaments that you lay down that are more on the nano scale, so a few hundred nanometers.
Right. There is a question about space, 3D printing in space. How would this work in a lack of gravity?
Yeah, so NASA is working on this exact question, I think, as we speak. There's 3D printers up on the International Space Station now, and we're working on some projects in collaboration with Virginia Tech in America, actually, looking at the effect on gravity. So yeah, very current and relevant question that we're working on.
Oh, it's very exciting. Now I see in YouTube. Thanks for the talk. Is it possible to anneal parts after printing to improve wheel strength?
Yeah, great question. That's absolutely what we do, particularly for the plastics that are semi-crystalline. So often in 3D printing, the parts cool down so quickly that you generally don't develop much crystallinity. And it's these crystal structures that can really help to bump up the strength of these materials. So that's absolutely a kind of a post-printing process that you can apply, is stick it into an oven to build up some crystallinity and really make these printed parts much harder.
Thank you. There is a quite interesting question. What do you call this combination of product design, 3D printing, and applying the use of math and physics?
Oh, yeah, do we need a new word for this? Yeah, I always call it kind of a molecularly aware model that we apply to engineering problems, because we can do this with other processes, right, as well as 3D printing. So yeah, maybe we need a cool acronym or something to get all those science words in there.
Right. There's another one. When printing for tissues, is there a chance for the body to reject the implant due to the foreign plastic inside the body?
Yeah, so I'm not a biologist by any means, but yeah, I'm sure this can happen. So this is one of the things scientists are working on, is trying to improve the properties of these plastic materials so we can avoid things like this happening.
And kind of a somewhat related question: how it's used for corals? Because they also need to like that plastic somehow.
Yeah, absolutely. Yeah, I don't know much about that application actually. Just that I know they were using the 3D printer because you can make such beautiful shaped geometries using the printer. So they were really trying to replicate the shape of real life coral. But yeah, I'm sure a lot of work went into finding the right material there that the creatures would like, I guess, in the coral reef.
Thank you. Just another one in Padlet. I'm just looking. With the diffusing of layers, if we had different colored layers, would be visible mix of colors between the layers?
Yeah, it all depends on how good your microscope is, right? Because when you get this interdiffusion process, so obviously we could see it in the slides on my talk, because we were really looking at a molecular scale there. And these polymer molecules, they're only about 10 nanometers in size. So yeah, you would really need a really good microscope to get down to that nano length scale to see the polymers diffuse. So yeah, very, very difficult thing to do, I think, experimentally.
I know what's mentioned, I think is question related to somewhere in your talk you mentioned good molecules. So this question, what are the good plastic molecules?
What are the good molecules?
Yeah.
I think what's really important in this application is the size of the molecules, because if you can increase the size, that basically gives you a better strength, because they're kind of more entangled with their neighbors. So you get a really good network of polymers. But obviously, if you increase their size, they're much slower, they're much more sluggish. So it really slows down this diffusion process. It makes them stretch out much more, and you get much more of this alignment in the flow. So there's kind of a sweet spot, definitely in the size of those molecules, which is really important.
Right. And there is a kind of generic question. Is it enough plastic for everything?
Is there enough plastic for everything?
Yeah, probably to print. Probably that was the question.
To print everything? Well, yeah, I think it's a recyclable material, right? To some extent. So potentially, yeah.
Right. So it is actually related to question of recycling and reusing. It's another question just arriving right now. Are the materials? I'm just waiting. Then the person will finish typing. Sure. Are you looking for other materials? Probably that is what.
Yeah, absolutely. We're always trying to push the boundaries of material diversity. So lots of people are interested in, particularly for the aerospace applications, is pushing up how high a temperature that these materials can withstand, and then trying to reinforce them. So yeah, always looking to push the boundaries of material diversity, kind of by adding additives to that plastic. So you can add carbon fibers to really give it more strength. and then going kind of down a more biological route, you can start thinking about.
Just you mentioned biological. The question now finished be typed. So it says, other materials like biomaterials, what you've been just mentioning.
Absolutely, yes. So there's a lot of work on biomaterials as well, and how we can actually 3D print cells.
Right.
So there's a very fine balance there of kind of wanting to squeeze them through the nozzle, but then not wanting to destroy your cell.
It almost reminds me movie Fifth Element when where kind of in movie the human in fact was printed.
Yeah, that's right, Andre. Yeah, I think the possibilities are just huge with 3D prints, and I think it's a really cool technology. Yeah.
Oh, thank you very much, Claire. So we answered quite a few questions, and was really pleasure to listen to this wonderful talk. And I just would like still to emphasize in the remaining minute that today is a special part of the of Lincoln Math and Physics Week, specifically dedicated to celebrating contribution of female scientists into math and physics, because today is International Women's Day, and we now find lots of female scientists contributing in all kind of topics, but not so long ago, just 100 years ago or less even, that was difficult. And Lincoln is a birthplace of famous mathematician in Victorian times, Charlotte Scott, who was born here, and she studied in Cambridge, but was not allowed graduation as female student. She became famous, though, mathematician, going to America and then coming back and spending lots of effort in promoting education for all genders. And now we kind of remembering that past, and we are really happy to have this celebration today and listen to Claire about her wonderful work on this really fantastic material coming, ranging from coral reefs, the human body, and even space. Thank you very much, Claire, for your talk. Very happy to have you this afternoon with us. Thank you.
Thank you.
And goodbye to everyone.